Hello, amazing students. Let's get to it. So we're talking about renewable and non-renewable energy sources, and I'm looking at this diagram here. This diagram is a little different. I believe our first diagram was 2017. This is 2013. Important to understand trends, but also try to understand that when you do the AP exam, the certain diagram that is there, they try to use the most current data. However, it takes a couple of years for a question to come out. So, and sometimes there's 3 years layover. So just be able to read the diagram. So important to know general trends, current trends, but also be able to interpret the diagrams that are in front of you. Okay. So let's look at this. One thing that jumps out at me, and it gets me big mad here, is that in 2013, total world consumption was only about 19% renewables. Unfortunately, we're still around that area, and that's total world. The United States does use a large portion of the renewables, but the rest of the world does not. There are multiple reasons why that might not uh, actually come to be. We could think of developing and non-developed countries, or developing and developed countries. And sometimes these technologies or the infrastructure to implement solar panels or electrical wires from one location to the other just don't exist, or there's no finances um, to finance these things. So anyhow, we do want to push for renewables, but this is where the data stands right as it is. Um, Now, what are some renewable energy sources that you should know? Well, you're going to need to know all of them. There's categories. Let's look at some of those categories. First one is, like, let's say biomass. It's a big term. It means so many different things. Bio, living, mass, anything that has living and have mass. It could be cow dung, trees. It could be corn husks that are fermented and turned into ethanol, which then could be used as a fuel. I use some big words there, but biomass means basically making some type of fuel source from organic material, something that was once living. Okay. So ethanol could be used or made from fermenting corn or fermenting any type of fruit, really. Um, and biodiesel could be a lucrative business. This is going to be using organic material to make diesel fuel. And so you're making an oil-like substance. There is a lot of technology now that's going out to pulling oil from algae and then converting that and making biodiesel. And there are cars that could actually use biodiesel. So that is something cool that the future could possibly exist. So when we're looking at here, traditional biomass, that's probably most likely going to be peat or wood. Okay, 9%. So that's the majority. Is that out of the total 19%, 9% is still wood. Still wood, still peat. And then we're looking at bioheat. I don't know what that might be. That might actually be like manure rotting, and we're remember I showed you the picture of the mulch and it was just generating heat. As decomposition occurs, the organic, as the material starts to decompose, it gives off heat energy. The microbes that are doing the decomposition process are going to give off heat energy. And so that may make up for that bioheat. Ethanol, like I said, the fermentation of organic material. Biodiesel, like we talked about already. Um, Biopower generation, maybe burning certain things. Look at our hydropower. We will talk a little bit more about that. That's like using the power of gravity and water, hydro water, to turn a turbine. Wind, we have solar, a bunch of different solars over here. Geothermal heat, we'll talk a little bit more about that, and that's going to be using the heat that's in the earth. And so we know, because we covered this chapter already, the inside of our earth is the core, then we have the mantle, then we have the crust. Well, the deeper we go in the crust, we're going to get closer to that mantle, the hotter it will get. Remember our hot pocket analogy. So in certain parts, the ground is warmer closer to the surface. And so if we dig some holes and put some pipes down there, and then as we uh, pump cold water down, the surrounding areas will warm those pipes, and we could continue to pump that water, and we may be able to produce steam. We may be able to produce warm water, and that could be used to generate electricity. Okay. And we have solar. So, really important to understand, only 19% of total world consumption, I believe, still around that number. Um, we need to do something about that. And we mentioned some vocabulary terms. We also talked a little bit more about biomass. Um, I like biomass as a fuel source. Uh, Let me take some time to discuss the pros and cons of biomass, though. So, one of the pros is that you would be carbon neutral. Let's try to think about that. You're still going to be burning biodiesel, similar to, let's say, regular diesel. So, CO2 is going to be produced. But here's the caveat to that: the CO2 that is being produced by organic material that sequestered that current CO2. So let's say if we used corn, right? To grow the corn is actually absorbing CO2 out of the atmosphere. Now, let's say we digested that corn and we made ethanol or we made some biodiesel. Well, now we're going to burn that and now release that carbon back. We're still at carbon zero. The issue with fossil fuels is that because we are using sequestered, stored carbon and now entering that into the atmosphere. So there are some I mean, that's a kind of a pro where it's carbon neutral. Okay, it still produces, um, greenhouse gases. It's still, well, but it's carbon neutral, so not necessarily. It's not going to produce as much sulfur as coal would, so that's a pro as well. The other big con is if we start using land mass. Arable land is the word. Arable is a really good word. Know that word. Arable means farmable land. If we now start to use arable land to grow crops for fuel, this is going to shrink the amount of arable land we have to grow crops. If that happens, the price of food can increase. And so, if the price of food increases, there could be widespread starvation. And that is a big issue. And so, the tropical rainforest in Brazil, the Amazon rainforest, is under attack through slash and burn agriculture, seeding agriculture. Imagine if they could now grow crops to make fuel. This could cause a positive feedback cycle in tropical rainforests and in forests in general, and that might not be a good thing. So that's a con of, let's say, using something like corn, and that's why I've mentioned before that there's some new technologies trying to harness oil from algae. I even saw an Exxon commercial, and I used to work with a doctor. Shout outs to Dr. Mike Azamik. Um, he he's a professor in Florida. Um, I don't know which school, but he was schooling me on the breakthroughs that they have on specific types of algae that produce a lot of oil. You simply squeeze them, the oil comes out, and then you can refine that oil and produce a fuel from it. So pretty interesting. The thing about algae is it's not going to take a lot of space. Like, it doesn't necessarily need arable land. You can grow it in plastic bags, and you could make a skyscraper straight up and down in little plastic bags. And so it's not going to take up so much space like a crop would need. Imagine a skyscraper of a bunch of algae bags. That would not take a lot of space up. It would be using a lot of sunlight, and algae don't need a lot of things. They don't need, dirt. They could just grow in a bag that has some water, and you just need some nutrients. And we have plenty of nutrients from runoff from our CAFOs. So it seems like a win-win situation in there. All right. Okay, let's continue on. And here are some images of how we could make electricity. I've explained how we make electricity before. Let's look at it in some of these images. This would be hydropower. And hydropower typically is going to be made by dams. Um, a dam is like a blockage of water you're going to have before the dam and after the dam. Dams are a huge thing that is brought up in the AP exam, because what really is important in life. I think there's three things: is air, soil, and water. Well, a dam controls water, so without water, life cannot really exist. So, but if we put a dam in a certain location, before the dam gets plenty of water, after the dam doesn't get a lot of water. Uh, this could also, I don't want to turn this into a dam conversation, but just understand that we'll talk about dams another time. But before the dam, eutrophication could occur. After the dam, wetlands can get dried up. And so we talked about how valuable wetlands are. And so all the nursery, all those valuable things that the wetlands can provide for us would be all dried up, usually through the formation of a dam. But let's talk about it in a renewable energy source type of way. Sorry, one more thing. Fish, salmon. Salmon have to swim upstream to lay their eggs back where they were hatched. Imagine trying to go back to your home and now you have this huge dam. That's something that they create a problem. So they affect the migration patterns of fish. Okay, so let's look at the dam. Before the dam, the water could flow. It's flowing from gravitational potential energy. And it's going to turn a turbine. That turbine is going to now turn a generator. You have your power to your transformers, and they can get powered to the rest of the homes or the buildings or the grid that is connected to it. Okay, so basically, here's your turbine. We're spinning the turbine. We're creating electricity. This is hydropower in a nutshell. In our next image here, we have a wind turbine. Okay, wind power, which is a renewable source of energy. And we're just going to use the power of wind to turn the turbine. That's going to power the generator. The generator is going to create electricity, and it'll be powered all over through the grid. So whatever can cause a spin is going to create electricity. So here's one we haven't seen before, and this is going to be nuclear power. And I'm not a nuclear physicist, but let me try to explain it in layman's terms so you completely understand how this thing really works. First off, you just need to understand there are certain things that are radioactive. What does that mean? That means they're not stable. They want to be stable. You could think of them as very reactive. You know, I can't hardly stand still. You could think of me trying to move all the time, and my wife kind of balances me out, makes me stable, kind of controls me. But just imagine a bunch of Iteries, and this would be radioactive material that's running around like crazy, giving off a lot of energy. And as they're giving off a lot of energy, they give off heat. So they could, anything that touches them is going to get warm through conduction. Okay. So let's look at it. So we have radioactive rods, control rods, and a reactor. Typically, we're going to take radioactive uranium. Uranium specifically is what we use. And when we put the uranium in a type of solution, that solution is going to get really hot. So this purple fluid in here is the solution that's getting really hot by dipping the uranium inside of it. Okay, this is going to create a flow, and now this hot liquid is going to warm when it's in a pipe. But imagine a very hot pipe, and then on top of it is like water. Well, when the hot pipe touches water, now that's going to cause the water to boil. So now we're going to have steam being created, and then that's going to turn the turbine. Then we have that word condenser coming back up. This is cold water. It's going to then cause the water to turn back into the liquid form, and then you could have it pumped back up again and again and again. So you have a pump here with this fluid, and you have a pump here with the water. And now when the steam turns to turbine, you get electricity, the generator, out to the grid. Now, one thing you need to understand about a nuclear power plant is that it could melt. It can melt down. And so usually there's a containment structure to try to control that radioactivity. And also, like this could get so hot where it could melt the concrete, it could melt the steel, it can melt everything, right? So it constantly needs to be kept cool. That's why the control rods are there. The control rods absorb some of that radioactivity, keeping it cool so it doesn't blow up. In addition to that, at nuclear power plants, you're usually pulling in fresh water from a reservoir, either a body of water, to keep the generator, to keep the turbines cool as condensers. It returns hot water to the outdoors. So imagine it's sucking in cold water and then warming it up, and then you're spitting that back outside. And now, so typically outside power plants, you're going to have a warmer discharge. So the temperature of the water in power plants, I'm going to say all power plants, coal, um, nuclear, particular, this is called thermal pollution. In Seahorn, I actually fish next to a power plant, and I'm not going to tell you where. You probably know where already, if you know it. And the fish probably sit there earlier in the season when it's still cold out because it's about 10 degrees warmer. Um, uh, so something to think about: thermal pollution is typically caused by power plants. All right, all power plants, but particularly thermal power plants. All right, let's continue. All right, the radioactive isotope specifically is uranium 235. So that's what you need to understand. We use uranium 235. It's going to be a great link. So hopefully you go back to the PowerPoint, look at that link for that. And we get this by enriching uranium 238. Now, I don't know what 235, 238. These are isotopes. What does that mean? That means they have uranium 238 has a couple more neutrons than uranium 235. Now, the 235 is the more reactive one that we use. How do we get that? Well, we're going to basically enrich uranium 238. Where can we find uranium? Uranium's in the ground. It's usually not in huge quantities, so we have to particularly refine it, find the particulars, put it all together, particles, put it all together, enrich it, and now we have it. Okay. Now, uranium is not radioactive forever. Okay, those rods can't the uranium in the power plant is not going to stay hot, commercially hot, let me say, forever. I believe they have a half life of something of 20 years. We haven't talked about half life yet, and hopefully I'll get that today. But basically, that means, let's say if they were 100% hot, and let's say 20 years is their half life. That means in 20 years they're going to be 50% hot. In another 20 years, they'll be 25% hot. So a half life is a known amount of time that it takes something to basically break down into half of itself. Let me break it down simpler. When you get a brand new cell phone, your battery is lasting great all day power, baby. All day power, and you're going hard. Okay. After the first year, does your battery work as good as it did it's when you first got it? No. Probably half of the day. And then you need to connect it to the charger. After 2 years, that your battery, everybody's thinking, I got to get a new phone. I'm living next to the charger. Some of you right now are charging your phone. Some of you got it plugged right into your Chromebook. Okay. Your cell phone's about 2 years old because the battery has a half life of about a year. That means out of 100% efficiency, after 1 year, now it's at 50% efficiency. After another year, now it's at what's half of 50, 25% efficiency. So your battery is almost nil. After 3 years, it'll be about 12.5. Whoa, 4 years? People who have their cell phones for a very long time, shout outs to those people. I know someone that has an iPhone, I think, yeah, iPhone 4, which I have the 12 right now, and I'm sad because I would love to be that person with the iPhone 4. Um, but how can they live with the battery that doesn't even last like that? Like they must just use their phone for calling. Um, I sound so, what's the word? Like a first world problem, so like disconnected from the reality of the world. I apologize. Okay, let's continue. So since the uranium 235, stays hot, but has a half life of 20 years. So after 20 years, it's at 50% efficiency. Another 20 years, so 40 years, you pretty much have to swap out the uranium. The uranium is not calm by any means. Um, it's still radioactive, but it's not necessarily commercially viable. So we'll either swap it out. So what do you do with this nuclear material? This nuclear material can be made into a big bomb and could dirty areas, making them radioactive, like Chernobyl, if they were just blown up somewhere. And so you need to secure this thing. So here's another fear of why they stopped having the nuclear power plants in the 70s is what do you do with the waste when it's done? Well, one idea that was pitched was to bury it in the desert, someplace called Yucca Mountain. Okay. And that's what they're typically are going to be doing. Hey, so this is kind of old technology, so I don't even want to spend so much time, but just understanding that what do you do with this old nuclear material? You can't necessarily throw it in the garbage can. This is hazardous waste that has to be stored for hundreds and thousands of years. So one idea was to bury it in the desert, the Yucca Mountain. Um, this would be cool because it's not next to tectonic rocks or it's not next to water. So that was pretty cool. But shipping all of your nuclear material one place seems a little dangerous. So this project never really took off. Um, it's an idea. What are we going to do with it? We don't know. Interesting thought, though. Like, when the human species is no longer here on Earth, the way we store our nuclear material, where it has to be some, our language may not be read. So imagine how we're going to store these things with like pictures or stuff like that. Just hazardous material. Anyhow, interesting thought. I'm coming to an end of the nuclear power. And remember how I was telling you that these power plants suck up cold water and then they spew out that warm water? This is what that would look like. And this would be a nuclear power plant. These are um, releasing heat energy. And there's no CO2 emissions, there's no air pollution with nuclear power plants. These are cooling towers. Um, so that is a pro because nuclear power does not necessarily create that. Now, here's a connection to water quality though. If the water gets warmer, it holds less dissolved oxygen. Okay. So this could decrease the amount of fish in that given area. I know I said before this is my good fishing spot. Um, but if it was shallow water and coupled with extremely warm temperatures, you could create a dead zone or a fish kill. All right. Okay, let's look at half life a little bit more. I might not have explained it well enough. I think the battery analogy was really good, but let's look at these practice problems as well. Okay, so for example, your cell phone battery from day one works at 100%. About a year works about 50% efficiency. In another year, it works about 25% efficiency. So its half life would be 1 year. In another year from that, it'll be at like half of 25%, which I believe is 12.5%. Another year from that, it would be 6.2%. Okay, so your cell phone continues to degrade. What's happening molecularly? Think of think of them as being very reactive, becoming stable. So batteries are charged, right? They have to give off electrons and so on and so forth. What makes them do that? They're typically, battery acid. Well, that battery acid, the longer that battery stays there, it becomes stable. So you want to hear a funny story? My dad is a truck driver, and trucks use big batteries. They use four huge big batteries, and battery acid is what powers them. So, let's say one day in a cold morning, your truck doesn't start. Old school Viteri dad would open up the batteries, put his finger in it, and taste it. If it wasn't sour, he would say, "Oh, the battery's dead." Basically, it became more stable, and so that acids are very sour. He would just like um, taste battery acid. Crazy. So Half-life is really, really important. You could use it for many different situations. You could think of it as the half-life of uranium, how long it has to be stored, the efficiency of the battery, the efficiency of a solar panel roof or PVCs. Um, you know, half-life is really important, and it's a known amount of time for something to break down molecularly into 50% of its quantity. Or we could think of it as efficiency, 100% efficiency to 50% efficiency to 25% efficiency to 12.5% efficiency, so on and so forth. Okay, we could look at it that way as well. Let's look up some more practice problems. Okay, so here I've seen some problems like this. Let's say we had 1/16th of the original substance. So how many half-lives have gone by? So we start with 1 over 1, right? That's the starting point. 1 over 2, 1 over 4, 1 over 8, 1/16. This is 4 half-lives that went through. Now, if each half-life in this problem is 10 years, that means 10, 20, 30, 40. 40 years has gone by. So that's the answer to the first problem here. If an isotope 1/16 is left over and each half-life is 10 years, 1 over 2, 1 over 4, 1 over 8, 1 over 16. What am I doing there? I'm just dividing it by 2 each time. So it's 1/2, 1/4, 1/8, 1/16. 4 half-lives. Each half-life is 10 years. That'd be 40 years. Right? Here's another one. The half-life of solar panels is 10 years. How many years will it take for them to work at 25% efficiency? Let's try to see that. So after 10 years, they're going to work at 50% efficiency. After another 10 years, they're at 25% efficiency. So the answer here would be 20 years for the second question. Last question. This is to deal with radioactive dating, and you can use half-life for that. Typically, when we're talking about radioactive dating, how old a fossil is or something like that, you compare two different isotopes, one that is stable and one that is unstable. The ratios you can take from those two is how you'll determine how old something is. So in this case, I'm going to use carbon-12 because that's a very common one that we do for aging. And the half-life of carbon-12 is typically 5,000 years. Okay. So we have 1,000 grams of carbon-12, and then it converts into let's say 125. So it breaks down into carbon-14. So we can think of it as the origination was 1,000. Now, how many times did it break down to get to 125? Well, if we start with 1,000, 500, 250, 125. So that was 3 half-lives. Each half-life is 5,000 years, so it's 5,000, 10,000, 15,000. So that fossil is approximately 15,000 years old. You want to pause this, you might want to look up a YouTube video and practice some half-life questions. You could also hit me up on Mind. I hope you learned something. I'll talk to you later.